Hello good people, it is time to bring a whole bunch of chemistry concepts together. I'm going to explore a problem where stoichiometry, density and molar calculations will all be needed. We are going to begin by dissolving a 29.5 cubic centimeter crystal of sodium hydroxide in water to give a 375 ml solution. We are also going to bubble carbon dioxide through this solution, which will result in aqueous sodium carbonate, as well as water. We know that the density of sodium hydroxide is 2.13 grams per cubic centimeter. We need to calculate the mass of carbon dioxide that can react with the sodium hydroxide. We also need to calculate the molarity of the sodium carbonate at the end of the reaction. There is no doubt about it. This problem is so hairy that even your ancestors might experience a slight tickling sensation at the back of their throat. Where do we begin? Considering that this is a reaction, a good place to start would be with the chemical reaction equation. And here it is. We will have sodium hydroxide in water reacting with carbon dioxide to give sodium carbonate and water. Now that I have my reaction equation, I need to check that it is actually balanced. And in this case, it is not. On the product side, I have two sodiums, whereas on the reactant side, I have only one. So I'm going to write a coefficient in front of sodium hydroxide. Now I have two sodium atoms on the reactant side and two sodium atoms on the product side. What about carbons? Well, I have one on each side, so that is good. In terms of hydrogens, I have two hydrogens on the reactant side and two hydrogens on the product side. When it comes to oxygens, there are 4 oxygens on the reactant side and 4 oxygens on the product side. So now everything is balanced. At this stage, it is a good idea to revisit what the problem is actually asking us to do. We need to calculate the mass of carbon dioxide and we need to calculate the molarity of sodium carbonate. I'm going to start with the first question and see if I can develop a bit of a roadmap. Alright, so at the end, I want to have the mass of carbon dioxide. That is what I'm trying to find out. Seeing how this is chemistry, most calculations will somehow involve moles. And so, to calculate the mass of carbon dioxide, at some stage I will also need the number of moles of carbon dioxide. And now I have a bit of a problem. The number of moles of carbon dioxide is not given to me. However, from the reaction equation I could say that for every mole of carbon dioxide I will need 2 moles of sodium hydroxide. Conversely, I could say that for every mole of sodium hydroxide I will get half as many moles of carbon dioxide. I can add that information to my little pathway. So now the question becomes how many moles of sodium hydroxide do I actually have? A common mistake would be to say that we have 2 moles of sodium hydroxide, because that is what is given in the balanced reaction equation. But keep in mind, this is just a ratio. I do not necessarily have 2 moles of sodium hydroxide. The number of moles of sodium hydroxide will depend on the mass of sodium hydroxide present. Unfortunately, the question is not giving me the mass of sodium hydroxide present. Instead, we have been given the volume of the sodium hydroxide crystal. How does the volume help me? Recall, mass and volume are connected via density, and that is something that the question has given me. And now, moving forward, I could say that I'm going to use the density of sodium hydroxide together with its volume to calculate the mass of the sodium hydroxide, which I can then use to determine the moles of sodium hydroxide, which I can then use to determine the moles of carbon dioxide, which I can then use to determine the mass of carbon dioxide. I did tell you, it is a hairy problem. Alright, this is the pathway for the first problem. What about the molarity of sodium carbonate? In order to calculate the molarity of sodium carbonate, I will need the number of moles of sodium carbonate. But I will also need the volume of the solution. How could I determine the number of moles of sodium carbonate? If I had the mass of sodium carbonate, it would be relatively easy. Unfortunately, the problem has not given me the mass of sodium carbonate. However, from the reaction equation, I can see that however many sodium hydroxides I will have half as many sodium carbonates. The reaction ratio between sodium hydroxide and sodium carbonate is 2:1, which means I will need this piece of information from the first problem. And so by solving the first problem, I will also have the information needed for the second problem. Are you having fun yet? I sure hope so. Now that I have established these pathways, I actually need to perform the calculations. I will need a fair amount of room, which means I need to remove all the things that I have written here. The only thing that I'm going to keep is the reaction equation, because that can come in very handy. Recall that the pathway for both problems required the calculation of the number of moles of sodium hydroxide. So that is a good place to start. And I can calculate that by taking the mass of sodium hydroxide and dividing it by its molar mass. Unfortunately, the problem has not given me the mass of sodium hydroxide. However, I have determined that I can calculate that from density and volume. These two components have been given to me. The density is 2.13 grams per cubic centimeter, and the volume is 29.5 cubic centimeters. According to my calculation, this will give me 62.8 grams when rounded to 3 significant figures. Now that I have the mass, I can use it to calculate the number of moles. And so I will have 62.8 grams divided by the molar mass of sodium hydroxide, which happens to be 39.997 grams per mole. And this will give me 1.57 moles of sodium hydroxide when rounded to 3 significant figures. Now I can use the reaction ratio to calculate the number of moles of carbon dioxide. Based on the reaction ratio, I will have half as many moles of carbon dioxide as I do moles of sodium hydroxide. And because I have 1.57 moles of sodium hydroxide, I can divide that by 2 to give me 0.785 moles of carbon dioxide. Using the moles of carbon dioxide and the molar mass of carbon dioxide, I can calculate the mass of carbon dioxide. And when I substitute in the values, I end up with 34.5 grams of carbon dioxide when rounded to 3 significant figures. We have successfully answered the first problem. The reaction will require 34.5 grams of carbon dioxide. Now we need to calculate the molarity of the sodium carbonate. And it will be the number of moles of sodium carbonate divided by the volume of the solution. The number of moles of sodium carbonate will depend on the reaction ratio. From the balanced chemical equation, I can see that for every 2 moles of sodium hydroxide, I will get a single mole of sodium carbonate. In other words, the number of moles of sodium carbonate is equal to the number of moles of sodium hydroxide divided by 2. Previously, we have calculated that we have 1.57 moles of sodium hydroxide, and that will be divided by 2, which will give us 0.785 moles. Now, we could have approached this a bit differently. The truth is that there was no need for this calculation. If I look at the reaction equation, I can see that the ratio between carbon dioxide and sodium carbonate is 1:1. In other words, however many moles of carbon dioxide I have, that is how many moles of sodium carbonate I should also have. Regardless, now that I have the moles of sodium carbonate, I can calculate the molarity. I can divide the number of moles by the volume of the solution. The number of moles is 0.785, while the volume of the solution was given to us in the problem, and it was 375 milliliters. Recall that for molarity calculations, the volume needs to be in liters. So I'm going to convert those 375 milliliters into 0.375 liters. And when I divide these two numbers, I end up with a molarity of 2.09 moles per liter when rounded to 3 significant figures. Now, before you underline and celebrate, there is a problem. This result is not correct. Why might that be? The calculation for the number of moles is fine. The problem is with the volume of solution. The given volume of solution was 375 milliliters or 0.375 liters. But the reaction itself will also generate water. We need to take that into account. How much water is being generated by this reaction? Based on the reaction ratio, I could say that for every mole of sodium carbonate, I will also get a single mole of water, which means the number of moles of water equals the number of moles of sodium carbonate. And I have already determined that the number of moles of sodium carbonate is 0.785. How much water is that? Well, by using the number of moles and the molar mass of water, I can calculate that. And when I substitute in the values, I get 14.1 grams of water when rounded to 3 significant figures. Usually, when we measure out water, we do not measure it out in grams, but rather in milliliters or liters. In other words, I need the volume of water. What links volume and mass? Well, it is density. And so to determine the volume of water, I'm going to divide the calculated mass of water by the density of water. And that will be 14.1 grams divided by 1.00 grams per milliliter, which will give me 14.1 milliliters. The total volume of solution will be the initial volume, 375 milliliters, plus the 14.1 milliliters generated by the actual reaction. So let me scroll down to perform the final set of calculations. And so now I could say that the volume of the total solution is 389 milliliters when rounded to 0 decimal places, or 0.389 liters. One more calculation to go, and that is the calculation of the molarity of sodium carbonate. We have the number of moles, 0.785, that needs to be divided by the total volume of solution, which happens to be 0.389 liters. And this will give me 2.02 moles per liter. And this is the answer to the second problem. You have made it to the end and thus earned a chocolate cookie. Ah, what a hell. Make it 2. That is all for now, and I will see you on the flip side.